All right, let's dive right into this explainer. Today, we're looking at an absolutely mind-blowing physics trick. It's a trick where changing just one simple thing lets a normal human hand effortlessly hold a massive amount of weight. We're focusing on a vital component of the hoisting system on a drilling rig, the brake band. Now, at first glance, a drilling rig's drawworks might just look like a massive spool of wire. But what is actually happening to control that incredible weight is an elegant dance of physics. We're going to explore how a seemingly basic piece of steel and friction material acts as an immense force multiplier, allowing an operator to control forces that should, by all rights, be completely impossible for a human to manage.
Picture this. You wrap a rope around a post, just once. If you pull on it, you can hold, say, 100 pounds. You're basically just using your own muscle to fight the load. But, and here's the brilliant part, if you take that exact same rope and just wrap it 3 times around that same post, you can suddenly hold thousands of pounds. Your input force? Exactly the same. You didn't suddenly hit the gym and become superhuman, right? The only thing that changed was the number of wraps.
That's literally 40 times the holding force. Now, this isn't some new cutting-edge concept. It's actually a centuries-old sailor's trick used to secure massive ships to docks. But what's really wild is that this exact same principle is what allows a driller's hand, just resting lightly on a single lever, to stop and hold a massive 300,000-pound load hanging over a 2-mile-deep open hole. It's a spectacular scaling up of a really simple mechanical advantage. So how does this actually work on the rig? Well, the equipment doing this, the brake band, is essentially a giant steel horseshoe. It's a long, flexible steel strap, and it's lined on the inside with these segmented friction blocks. One end is permanently anchored to the rig's frame. The other end, that's attached to a linkage the driller physically pulls with a handle. When they pull that lever, the band tightens around the brake flange and just squeezes that massive drum to a dead stop. This entire concept has a name. It's called the Capstan effect, and it is arguably the most elegant piece of physics on the entire rig. When we talked about wrapping that rope around a post a minute ago, we were describing the Capstan effect. As that steel band wraps around the massive spinning drum of the drawworks, friction is generated along the entire length of contact. And here is where the magic really happens. That friction along the wrap continuously adds to the tension. Now, what's truly fascinating here is that the band amplifies the driller's strength exponentially. It doesn't just replace their hand force. Tension doesn't just add up piece by piece. It multiplies. So you pull on one end with, say, 100 pounds of force. But because of the friction captured under that wrap, the anchored end of the band can be carrying thousands upon thousands of pounds. The brake band isn't doing the work instead of the driller. It's taking the driller's physical effort and multiplying it on an exponential curve.
Moving on to Part 1, Directional Application and the Self-Energizing Design.
You see, engineering isn't just about the parts themselves. It's about how they interact with forces in the real world. The design of a rig's brake band takes that exponential capstan effect and uses the rotation of the load itself to generate even more stopping power. Because of the way the drum rotates under load, it physically drags the band tighter. We call this being self-energizing. A really light pull from the driller lets the drum's own rotational mass drag the band snug, creating just an enormous clamping force right in the direction that matters. But if you turn the drum the other way, the exact same band is dragged looser, and the grip drops like a rock. This directional reliance is baked directly into the design. It's why you will absolutely never see a Drawworks brake band installed backwards. If you did, you'd instantly lose all that self-energizing multiplication. Now let's look at Part 2, Maintenance and the 3 Silent Killers. Here's the thing though, exponential physics, it's a double-edged sword, and it ruthlessly punishes tiny maintenance errors. When a system relies entirely on multiplication, well, any small loss of friction gets multiplied too. Remember, we are talking about stopping 150 tons of steel. If the friction material isn't in absolute peak condition, the math starts working against you fast. There are basically 3 ways your braking power silently dies. First up is glazing. This is when the lining overheats, gets completely glassy and smooth, and just flat out stops gripping the steel. Second is heat checking. That's when the steel flange itself develops this crazy spiderweb pattern of cracks from extreme thermal cycling, heating up and cooling down over and over. And third is contamination. Literally just a single leaking seal spraying a tiny bit of water or oil onto the band can drastically cut your friction. So I want you to think about this question for a second, based on what we've just discussed about friction and surface area. If only 2 friction blocks wear down on the band, why can't we just swap those 2 out instead of the whole set? I mean, it seems like it would save a ton of time and money, right? Why not just pop out the bad ones and leave the mostly good ones alone?
Think about what that would actually do to the physical contact inside the drum. Well, the answer is that uniform thickness sets contact. If you mix new thick blocks with old, worn, thin ones, the drum is only going to physically touch those new thick blocks. Instead of the massive load being shared across the entire surface of the brake band like it's supposed to be, a tiny fraction of the surface takes absolutely all of the heat and pressure. Those few blocks are going to overheat, glaze over, and fail incredibly fast, causing your total braking force to just completely collapse. That's why it's an unbreakable maintenance rule. You always replace them as a complete set.
This actually brilliantly illustrates our core concept, scaling the exact same survival physics of a mountain climber's belay up to massive industrial weights. Think about it. A belayer holds a fallen climber, not because they are vastly physically stronger than the person falling, but because they are leveraging rope friction through a metal device. Literally, one hand can hold a person's full body weight in free fall. The rig brake band is doing the exact same thing, just on a much larger scale. It's friction, not brute strength, doing the heavy lifting.
But because this effect is exponential, a slightly worn lining or a single drop of water doesn't just reduce your braking by a few percent, it can literally have it. Imagine a driller pulling that full stroke lever, fully expecting to stop 300,000 pounds, but the brake has been compromised by just a tiny amount of oil. That loss of friction drops the multiplier completely. The lever feels exactly the same in the operator's hand, but the massive load, it just keeps moving. Let's wrap up with this pretty stark reality. When you're dealing with an exponential force multiplier, a drop of oil isn't just a mess to clean up on the rig floor. It's a catastrophic failure waiting to happen. The smartest, most elegant physics on the entire rig can be completely undone by a single leaking seal. So I'll leave you with this to think about. In a system where the difference between safely holding 150 tons and dropping it all relies entirely on having a pristine surface, how much can you truly trust a simple visual inspection? Until next time, keep looking deeper into how things actually work.